Welcome to everyone to this Friday talks of the ANH. Today, we are glad to present our special guest in our ANH workshop number 34. Today, we have with us Dr. Brian Frost with a special talk about the petroleum prospectivity, potential and risk into the ultra-deep water of Colombia Basin. So this is a quick reminder of the different talks. Remember that last week we have a quite interesting talk about the global energy crisis as an opportunity for Colombia. Today, as mentioned before, we have the petroleum prospectivity, potential and risk in the ultra-deep water of Colombia Basin. Next week, we'll have a special guest as well, Dr. Karina Rodriguez from Searcher. She works currently from London. And it's a very special update about the seismic reprocessing that have been done into the Sinú San Jacinto onshore. It's quite special because, as well as you know, it's a bit easier to perform reprocessing into the deep marine setting, but they are working with those mode diapirs, to those possible mode diapirs into the onshore area of the Sinú San Jacinto and how to improve the seismic imaging. On October 28th, we have our number 36 workshop with a special guest, Carlos Molinares, Dr. Carlos Molinares, talking about the enhanced oil recovery for a hard stack of increasing production of the reserves in Colombia. As well, we'll have in November 4 different talks. Our first talk of November will be with Dr. Stephen Leslie, with the structure, stratigraphy, and petroleum potential of the deep water Colombia Basin, offshore northern Colombia. We'll have as well on November 11th, our special guest, John Munoz, Dr. Paula Arcila, and Fabian Gallego, with a quite interesting talk about the different structural styles of the Colombian Caribbean offshore and the relationship with thermogenic hydrocarbon evidences. It seems, and it's quite likely, that we will have, and we're quite glad to have Cesar Patiño on November 18th, talking about the hydrogen and geothermal energy for this transition that we're glad to have here into, or we start to perform and to study here into the NH. And as well, we have on November 25th, the workshop number 40 with our special guest, Martha Vides from INVEMAR with offshore Colombia. What type of biodiversity holds underneath? This is quite interesting. Not everything is not geology. We need as well the whole environmental thing about to understand how the nature of the Colombia offshore works. So those are different areas that have been identified during the year. 30 areas already identified, most of them into the Sinú San Jacinto and to the lower Magdalena Valley related to gas and condensate. And we would like to remind to all of the attendees in the link, you have the different presentations that have been presented during the year and as well in last year, because now I think we have more than 60 talks that we have been carried out during those couple of years. Today, we're quite happy to introduce our speaker of today is Dr. Brian Frost. It's an extensive career, but it's quite interesting to have you here. So Brian graduated from Colorado School of Mines in 1978 with a bachelor degree in geophysical engineering. He started his career interpreting and processing seismic data for Phillips Petroleum and learning how carbonate and clastic petroleum system work. After 12 years at Phillips, he moved on to Conoco and for the next 8 years evaluated frontier potential petroleum systems in Africa, Gulf of Mexico, the Caribbean, and the Atlantic margin. It was an exciting time to be exploring the deep-water petroleum system. Discoveries in the Gulf of Mexico proved deep-water clastic phases were capable of producing at well flow rates above 20,000 barrels of oil per day, which mitigated the high cost of deep water field development and combined with a high fidelity 3D seismic and seismic attributes to lower exploration risks. After Conoco, he joined the small independent British Borneo, who had 2 active deep water rigs under their contracts in the Gulf of Mexico and was looking to expand internationally. Small companies that act quickly, and over the next few years, new opportunities were captured in offshore deep water of Mauritania and the Santos, Campos, and Amazon basins of Brazil. British Borneo was a partner in the Chinguetti oil discovery, which opened of a new petroleum system fairway in offshore northwestern Africa, which industry is still pursuing today. In 2000, Brian joined Anadarko, who had just acquired 3 deepwater blocks in West Africa and looking for more international opportunities. They were a large independent with mostly domestic onshore and Gulf of Mexico operations, but also had a huge onshore oil development in Algeria. Their hands-on CEO was not afraid to take calculated risk, was mindful of cash flow constraints, and looked after the welfare of his employees. Over the next 18 years, the Anadarko International New Venture team successfully acquired deep water opportunities in West Africa, East Africa, and South America, resulting in world-class discoveries in Ghana and Mozambique. After 40 years exploring 13 basins, he retired in 2018 and now anxiously awaits the results of the yet-to-be-tested play. And he and his team developed in Peru, Guyana, and especially the Grand Cold blocks of Colombia. So, with no further than that, I would like to give the stage to Dr. Brian Frost.
Come on. There we go. Thank you, Danielle. Good morning, ladies and gentlemen. Today, I'm going to talk about the Grand Cold Basin, its petroleum prospectivity, potentials, and the risks as I see it. In 2012, Anadarko participated in a roundup that the ANH had. And it's when we got our first blocks in Colombia. And then in round of 14, they started to offer blocks in the Grand Cold Basin. And we were very pleased with the seismic data that we saw there and started to put together a story for how the petroleum system works in the Grand Cold Basin based on the regional 2D data that the ANH shot and the additional data we acquired in our TEA blocks. And this is a result of a modified presentation that I gave back in 2020 with the AAPG. This is the Greater Caribbean area. And as you can see, let me get my pointer here. This is the topography and bathymetry in the area. And it's also showing the exploration wells that have been drilled in the area and some of the big fields. Green is oil, red is gas. As you know, in it's hung up, there we go. You have the east of Venezuela Basin, 300 billion barrels equivalent recoverable. The Maracaibo Basin, 70 billion barrels of oil recoverable. The Columbus Basin with 5 billion barrels of oil recoverable. Cuba, 10 billion barrels of oil equivalent. And Guyana, 12 billion barrels of oil equivalent. What's really missing here is anything in the Grand Cold area. Here we go. Okay, so we're going to talk about the Deepwater Magdalena fan. I mean, it's a really good place to be hunting, but you can see there's a definite lack of wells anywhere in the ultra deepwater Magdalena fan. So, and when you're doing frontier exploration, you have to see where you've been, you have to see where you are, and then you have to decide, well, where do you want to be? So what do we look for in a frontier petroleum system? We want good source rocks. We want a good sedimentary section on top of those source rocks in order to mature them and to get them starting to generate petroleum. We want good reservoirs. In deep water, mostly we're looking at clastics, sometimes carbonates. And then we want all the timing for the deposition of the source rock, the reservoir, the maturation, and the traps to all occur in the proper order. So that's kind of what I'm going to show you today about the Grand Cold. We're going to concentrate in this the new box here and take a closer look. So you can see here the existing discoveries, some of the important wells that have been drilled. The original deep water well in Colombia was drilled approximately at this position here. That was in 500 meters of water. It was not successful, but industry was running out of places in the rest of the world, and this was still pretty much a virgin basin. And of course, that attracts people to start finding out more information, drill wells. And you can see the discoveries, the existing discoveries, Chupa Bolena. Things really took off when Repsol and E&I found the Perla field in Venezuela. And the reason it was unusual is that everyone thought that this was a gas province without any liquids potential. But Perla proved up that there was significant liquids potential, almost 100, 200 million barrels of condensate. So suddenly, instead of this being a dry gas area, it became interesting that we might be able to find some liquids. Anadarko picked up acreage down in here in around 2012 and in the Magdalena Fan in 2014. And we started drilling our wells. We started to find dry gas in Purple Angel and Gorgon. There's still some untapped potential in here remaining, most likely going to be gas. Industry found gas in Orca, other wells along this coast. Callisu was a really important well Anadarko drilled because it proved up that in the deep water Magdalena Fan, you had incredible reservoir potential, maybe too much reservoir close in. Hopefully, as you get further out to deeper water, the sand shale ratio becomes more shaly, and perhaps you got better seals. Some other important wells that were drilled early on were in Costa Rica here, the Morote and Manzanillo wells. These were based on, well locations were built based on outcrops. They were only about 600-meter wells. They didn't find any petroleum, but they found incredible source rock. DSDP 153 was drilled out here in ultra deep water. The DSDP wells are not designed to find hydrocarbons, but to explore the geology of the ocean basins. But DSDP, what was interesting in the Campanian through Cenomanian condensed section, found some good source rocks. They weren't very thick, which you would not expect on the clip that sits out here, the Caribbean large igneous province. But the fact that they found any source rocks at all was very encouraging. Let's see. Here we go. There's an interesting feature in here, this Hess escarpment that separates the Southern Caribbean from the Northern Caribbean. And that puts these Manzanillo wells in the same part of the Caribbean, if you will, as DSTP 153 and where the Magdalena Fan is being deposited. We're going to look a little bit more closely at the Bouguer free air gravity anomaly. You can see the Hess escarpment really sticks out and separates things from north to south. We're going to zoom into where these two wells in Costa Rica were drilled in the Nicoya Peninsula. And I highly recommend any petroleum geologist to take a look at this area in more detail. This is a USGS geologic map. The purple that you see here are pillow basalts. This is oceanic crust. But what makes this area so unusual are these Cretaceous sediments found on the top of it that outcrop. And this is the Lomo Chimico formation. And the next slide, I'm going to show you what it looks like. These wells, 400-meter well and a 600-meter test, show absolutely incredible source rock potential. There was a really good article by Elric and published in 1996. I highly recommend you take a look at. That's where these slides came from. And also some work that an Amico geologist did, Clifford Walters, evaluating the source rock potential of this Lomo Chimico formation. And basically what they found in two continuous core holes, these Cenomanian to Campanian age rocks. They were laminated to massive bedded siliceous, organic rich shales and chert, asphalt tuffs, volcanic beds, and organic lean cherts. So these rocks are telling you about a source rock environment that's very rich, but also has periods of where it's barren of carbonaceous material, in an overall volcanic clastic ocean spreading center. And the environment I'm envisioning is a place where you have a lot of volcanic activity. The volcanic ash is rich in nutrients being washed into restricted basins, and these nutrients are feeding the organic material, and the basins are restricted, and so you have anoxia. And what you're doing is you're accumulating a massive quantity of organic material. So what these wells found were 85 meters of type 1, type 2 kerogen, 15% average TOC, with a maximum of 33% TOC, hydrogen index up to 900, very low oxygen index, over an area of about 25 by 60 kilometers outcrop. And what Clifford did was he took these source rocks and said, well, what are they going to generate? And he came up with a generative capacity of 4,000 barrels per acre foot of generative capacity for these source rocks. It's an incredible number. He also found thermophilic archaea bacteria, suggesting the depositional environment occurred in a hydrothermal environment, which is basically telling you that these are fantastically rich source rocks deposited on oceanic crust. I've never seen anything of this magnitude, basically at outcrop. But if you think about the Gulf of Mexico being an incipient ocean basin opening up, it's that kind of environment. If you look at West Africa, between the transform faults in the equatorial region and the volcanic centers to the south that created the salt basin as the mid-Atlantic basin was starting to open up, you had volcanoes generating volcanic ash in the oceanic spreading center, but you hadn't let the oceans in yet, which is why you also had a salt basin. So they're incredibly rich potential source rock areas in these incipient open basins. And I think the Caribbean Basin was an ocean that was trying to open and eventually failed. And that's why the Loma Chimico Formation is illustrating at surface what these rocks are, which we've never actually drilled into in the Gulf of Mexico or the petroliferous parts of the mid-Atlantic basins. And here you have it sitting in an outcrop, and it's telling you that these can be very, very, very rich environments. Okay, so we were just looking at this area down here, this Tempisky Basin. I'm calling it, this is this 30 by 60 kilometer basin. This is where these absolutely world-class source rocks have been found. Here's DSDP 153. And the 2D data that the ANH has acquired out in this region of the Grand Coal Basin has identified what I'm calling source rock pods. These are things I think that the Tempisky Basin must have looked like sitting out here underneath the Magdalena fan. And these source rock pods, we'll zoom in. Now we're looking at the bathymetry and topography. Here's the coastline back here. You can see the Magdalena fan are sitting on top of these source rock pods. And the Magdalena fan thickness gets up to 10 and 12 kilometers. So now you've laid this plastic-rich system on top of what could be a potentially world-class source rock. And I think the result of that, we'll look at some cross sections through one of these source rocks pods in this AA prime. Then we'll look at a regional cartoon of what the ANH seismic data looks like. And then finally, I'm actually going to show you one of the ANH seismic lines from 212, line 6. Those were part of the data package of Rhonda 2014. And it was absolutely stupendous data quality for 2D data. And I think one of the reasons that makes the data quality so good is the water is very deep. And so the fidelity of the seismic data is just excellent. And what we'll do first is we'll look at AA prime to show what one of these source rock pods looks like. You can see oceanic crust. It's relatively thin out here. And you have these source rocks deposited in here, and you can see this incredible differential compaction that's occurring here, which is telling you that the sediments that are filling it are not sandstones or they're very squishy sediments, right? Which is what you'd expect in a source rock environment. They thin on all of the basement highs. You also can see that the turbidites from the Magdalena fan are actually still compressing these source rocks and creating these compaction faults, which I think are acting as the migration pathways, getting the hydrocarbons out of these source rocks and up into deep water clastic reservoirs, or deep water clastic reservoirs. Okay, so one of the key problems with that, or not a problem, the key differences of the Magdalena fan from the Gulf of Mexico. In the Gulf of Mexico, you have your sediments traveling from their origin up in the mountains of the Rockies, almost 1,500, 2,000 kilometers to the Mississippi fan and being deposited in the Gulf of Mexico. So in that transport distance, most of the reservoirs, you'd call them quartz aeronites in the Gulf of Mexico, because basically they were all just sand, quartz, enveloped in shales and with the occasional volcanic ash. In the Texas part of the Gulf, you get a little bit of carbonates mixed in with the sands, but you have a very clean system. So that what they worry about in the Gulf of Mexico is overpressure from shales and quartz overgrowth, right? Because you've got a lot of quartz in the system and it's very deeply buried. And so that's going to be your main problem with porosity and permeability with depth. All right. Compare that with the Magdalena fan, where your provenance areas are draining areas very rich in volcanic sediments and also siliceous sediments or reworked Cretaceous sediments, all being transported by the Magdalena out into deep water. That's what causes the beaches in the Caribbean part of Colombia, get black sand beaches, is because there's a lot of lithic fragments in the sediments being transported by the Magdalena. I mean, it's not totally volcaniclastic. It still has a lot of sand in it, siliceous sands, but it's mixed. What happens when you deposit those sediments in deep water? Initially, the reservoirs act like any reservoir. You have high porosity, they're well sorted, but these lithic fragments that are also deposited, as you bury them deeper and deeper, the lithic fragments are the first to break down, and it creates clay. And those clay particles through flow get transported to where the pore throats are in the rock and start plugging up the pore throats. So one of the issues about the Magdalena fan is that as you bury the deepest reservoirs like you're seeing down in here, those pore throats are going to get clogged. And that's why I think, like when we drilled the Kalamazoo well, we had really rich sands, we had good porosity, but we started to hit pressure. And the pressure kept increasing the deeper down that we drilled. And I think that's a sign of the pore throats being clogged with depth of burial. I think that's a good thing and a bad thing. It's a good thing in that these source rocks that are generating, these reservoirs down here close to the source rock have already had their permeability occluded by these clays from the lithic fragments. So you can't fill any pore space down here with the hydrocarbons. It's forcing the hydrocarbons to move up these faults into shallower horizons where you still have good permeability in the reservoirs. And what we noticed on the AVO response of the deep water sediments in the Magdalena Fan was we had really good class 2P AVO response in the sediments. So we're down to about 2 kilometers or so below mudline. But when you got deeper than that, the response started to go away, which I think is a function of well, basically you're not filling any of those deeper reservoirs with any hydrocarbons because they're all escaping and migrating up into shallower reservoirs. Okay, the next slide we're going to look at is the long regional slide to show you where the anomalies are. So this is 150 kilometers. This is absolutely spectacular seismic data going from just at the edge here, at the toe of the slope of the Magdalena Fan. And there's some really curious things going on here. All right, these are all the deep water sediments moving away from the Magdalena Fan, but you ask yourself, okay, they're dipping landward. Why are they dipping landward? Sediments roll downhill, and you can see that the seabed that you're dipping seaward. And what's happening is you're loading the crust back here with the Magdalena Fan, and horizons that were originally dipping in a seaward direction the dip is reversing because of the weight of the Magdalena Fan on the crust. Okay, what does this do? Our source rocks are sitting down here. This is our faults caused by differential compaction over these basement highs. These are the grobens within between those basement highs and the oceanic crust. If you were to tilt this thing and lay it flat, remove the Magdalena Fan, basically you'd be looking at the clip section sitting over here. I'm not sure what's going on this side because it's running off the section. That's interesting. Anyway, and as you're filling this thing up and loading it, you're migrating your hydrocarbons out of the source rock, traveling up these faults, and it's creating these humongous BHI anomalies. The biggest one that sits out here is actually at the base of the gas hydrates, the BSR. And you can see from the scale of this, it's almost 50 kilometers, 60 kilometers wide. And in length, I think it's almost 300 kilometers in length. I mean, it's a huge anomaly. These other ones are more structural anomalies caused by the wrinkling of the Magdalena Fan sediments. But these things are massive. All right, I'm going to actually show you now a seismic line. This I got from the ANH. It's in their database, and you can go to the ANH data room in Bogota and take a look at this data, as long as it's an open acreage. If the acreage is held, then you can't look at the data that's within that area. But this is what it looks like. Here's the Caribbean large igneous province. Here's our really thin oceanic crust. This is the scale bar down here. These are the Miocene to recent Magdalena Fan sediments. These are the gas hydrates. This section is not really good for looking for DHI anomalies because it's just normal process migrated 2D data from the original processing. Reprocessing this data, you get a really big uplift in fidelity and AVO response. And I highly recommend it if this data is open and available. You request the tapes from the ANH and reprocess it yourself, and you'll be amazed at what it looks like. Also, as a plug, I guess, to ION, they've gone through and they've reprocessed a lot of this ANH vintage and more recent vintage of data, and the data is quite spectacular. Okay, so here's these pods. As this ocean basin failed, started to sink, the last parts to sink were sitting up on the far left. And here, I think you've got some carbonate plays in addition to the deep water clastic fan plays sitting up dip from these pods, which from an AVO response point of view, look to be within the main oil window also. So as this basin was initially filling, I think it was subaerially exposed. You didn't have, it's an ocean, it's an incipient ocean basin, but there's no ocean in it. And there's no ocean in it because you had the clip to one side, something was sitting to the other side and created a restricted basin. There's no evidence for salt in this basin, but you can see, well, I'm going to zoom into here. You had these in between the volcanic highs, you had these very deep basins filling up with this initial fill of sediments that's very compactable. And that's what I think is the Lomo Chimico formation. Then you let the ocean in, and you got this other series of sediments that may have been contemporaneous with carbonates being deposited on the cliff. Eventually, the carbonates drowned and ended all up in deep water until beginning of Miocene time. The Magdalena fan started to prograde and fill the space, which in turn provided reservoir and seal pairs and matured our source rock that migrated up the differential compaction faults in these Magdalena fan sediments and filled them with hydrocarbons. Okay, we're going to zoom in now to this area in the first slide, and in the second slide, we'll zoom in and take a closer look at the seismic data here. So here's what those pods look like, and you can still see the difference in compaction in them, the little hard bits of oceanic crust. And you can still see this differential compaction going on even up through these sediments until they're finally the Miocene to recent Magdalena fan fills everything in. You can see the compaction faults over these basement highs, providing you migration pathways and creating structural traps. And then when Anadarko shot a big 30,000 square kilometer 3D survey out here, you get these DHI anomalies also in stratigraphic traps. So you see so many DHIs in here. One of the main reasons Anadarko went straight to 3D was you always wonder if these DHIs, do they conform to structure? And there's not a lot of structure out here. So you don't know if your DHI is being formed by a structural configuration or by a stratigraphic configuration. And what we found by shooting our 3D survey was we could take the DHI anomalies and fit them into a stratigraphic, individual stratigraphic profile of stratigraphic trapping potential also. And these features were large. They were of thousands to tens of thousands of square kilometers of closure, which we'll get to, and I'll show you in a bit. I don't have the seismic data to show you, but the ANH has got the seismic data to show you. Now think about what's sitting in these pods. It has if it's like the Lomo Chimico outcrop, it's got a generative capacity of 4,000 barrels per acre foot. And I think that these pods are probably even more rich, if that's possible, than what was seen in Costa Rica. And some back of the envelope calculations just to show you what how much hydrocarbon could be generated from the thing. If you take the average thickness of these intervals is about 200 meters over a 30,000 square kilometer area. Looking back at the Loma Chimico, it's a 19% net to gross. That gives you 38 meters of net source rock that has this generative capacity. That means that this source rock could have generated almost 4 trillion barrels of oil. That's its generative capacity. So there are so many DHIs in this data set in the Magdalena fan clastics. Is it possible? And I think based on what we know about the Loma Chimico, what we see in this seismic, it's entirely possible. And we have the DHI, the quantity and quality of the DHIs to give us a check on if this is a reasonable estimate. What we don't have is any well to know what the rock properties, what the fluid properties are in those reservoirs. We'll talk about risk in a minute. Okay, this is that area showing the carbonates. That's our blue infilling above the Loma Chimico equivalent. You can see the stratigraphic pinch out here. You can also see the buildups. Scour surface, the buildup sitting back in here. So I think there's a valid carbonate play sitting out here also. And remember that the Loma Chimico just down dip from here is in the oil window. And we got DHIs in the clastic sediments to show that it's migrated through it. Okay, this scour surface I found really interesting. You've got carbonates back here from the DSDP wells that we know about in the Caribbean. And it makes me wonder, maybe this is our top Cretaceous, and that the scour surface may have been formed sometime in the past, like related to Chicxulub, I don't know. But the seismic data is of such fidelity. As more data is acquired, we'll find out more about what's going on out here. But for someone that does frontier exploration, you get a lot of freedom to suggest possible scenarios for what you're looking at. Okay. Let's talk about the risk and what we have out here. We've got stacked channelized turbidite sands over a 1,500 meter gross interval that come in packages, 40 to 60 kilometers thick, 5 to 7 kilometers wide channel belts. These are all coming out of the Magdalena fan, and that's basically what's making up your reservoir seal pairs in the clastic sections. You have a dip and combination stratigraphic traps, 4-way dip closures up to 200 meters, combination traps of 200 to 400 meters dip closure. You've got this base hydrate seal on all the shallowest reservoirs, formed by landward dipping turbidites, subcropped by the base gas hydrate regional seal. You've got, I'm calling these possible because we don't have any wells out here to calibrate them. You have possible direct hydrocarbon indicators. You have regional discoveries that have DHI expression. These anomalies track structure and stratigraphy, and there's flat spots. So you're getting up to really, really good direct hydrocarbon indicator quality out here. Reservoir quality and quantity. Callisu 1 basically proved up reservoirs out here. And one of the problems we discussed earlier was the lithic fragments are going to reduce perm with depth. A hydrocarbon phase is a huge unknown, right? Or all of this may be a huge petroleum province, but have all the liquids been converted to methane? I mean, that's what we need wells to find out. Or if it hasn't all been converted to methane, what's the API gravity of the liquids? In Venezuela, you have the East Venezuela Basin, 300 billion barrels of oil equivalent. Most of it's tar. They can still produce it. It's very heavy, but 14-degree API oil is not going to flow in deep water because the reservoirs are relatively cold. But you can have 18-degree API oil, which is biodegraded, but will flow just fine. The reduction or increase in viscosity is not very significant. So this is why we need to get some wells drilled out here to find out. Okay, let's go back to our thick source rock pods. You can see the seismic line we looked at, our cross section, and what the pod looked are illustrated here on this bathymetry and topography map. There's your thick source rock pods. This is what I think is the likely area of there being some source rock potential. Might be bigger, might be smaller. It's just my guess. Up here, you're kind of limited because you get back onto the large igneous province and there's really no room to have any of these source rock pods. To the south, I didn't really see these things expressed over here. This is the size of the polygons. You can see by just taking a look at the AVL responses on this data. I didn't ever have access to the ANH's 2014 survey, but of course we had the 3D survey that we acquired out here. So these are pretty well-defined anomalies. But this base hydrate seal is 300 kilometers long by 40 kilometers wide. It's just immense. You've got, wherever there's, you saw seismic lines, you can see direct hydrocarbon indicators with faults directly tying you to the source rock pods beneath you, and small offset faults directly feeding these potential direct hydrocarbon indicators out here. You've got a lot going for you. All right. So how does this petroleum system work? We've got the Caribbean plate moving this way, South America plate going this way, the El Pilar fault here, the Oca fault here. You've got thrust faulting on the south side of this transform fault, creating structures in the East Venezuela Basin, creating structures in Maracaibo Basin. We've got the same effect happening up here, thrust faulting from caused by a plate drag, creating incipient faults up here in the Magdalena Fan. We've got all these direct hydrocarbons indicators or potential direct hydrocarbon indicators here. I've got a cartoon cross section through the East Venezuela field and a cartoon cross section BB prime through Maracaibo and the Magdalena Fan here. If you take a look at East Venezuela in cross section, the Caribbean fault or Caribbean plates overriding the South American plate, your La Luna source rock was being depressed and filled in by sediments from the Orinoco River, tilting the whole basin, maturing the La Luna source rock, and oil migrating up dip, being exposed to the surface, and you get the massive tar belts of East Venezuela. You also have the thrust structures here giving you the El Furial field. So it's a relatively, in a big picture point of view, simple petroleum system. Okay, compare that now with the Caribbean plate and South American plate through Colombia and the Maracaibo fields of Venezuela. Here we have our La Luna / Loma Chimico equivalent source rocks. La Luna back here, it's a shallow water, relatively shallow water type like source rock. Here you have this Loma Chimico equivalent sitting out on oceanic crust. This would be the clips and seaward dipping reflectors we see out here. All right, you have the Magdalena Fan prograding out into this basin, depressing the crust, creating the El Furial equivalent thrust out here. This would be the equivalent of the East Venezuela field. And what's really interesting here is the gas hydrates are creating a regional lid on this entire basin. And the implication of that is that as we're loading this basin, we're maturing the source rocks out here. We're reversing the depositional dip. So by the time oil's being generated in these base little source rock pods, the dips have all reversed. So your oil migration is in a seaward direction. As you hit a permeable layer or hit the faults, you migrate in a seaward direction because that's your regional dip. However, when you get out to the farthest extent of where the oil is going, now we're biodegrading that oil into heavier oil and expelling gas. The basin has an ultimate top seal, that's the gas hydrates. And the gas hydrates should form at about 400 to 500 meters below the mud line. The mud line is dipping seaward. So you got a seaward dipping hydrate seal that's counter-regional to the regional dip, the regional depositional dip of the basin. So hydrocarbons moving up, where if gas is generated, it's going to be frozen as a hydrate in the first 300 to 500 meters of sediments. But then below that gas, you're going to have free gas, and that free gas is going to be trapped by the hydrate seal, and it will be migrating up dip, which is in landward direction. And I think that's why you find so many shows of gas close to the shoreline in the Magdalena Fan, dry gas, but it's not dry gas of biogenic primary conversion of organic material into methane gas, like what you'd find in complex organic molecules. It's biogenic gas created from the biodegradation of oil. That's my belief anyway. Okay, let's keep going. In summary, oil's where you find it, not where you'd like it to be. You've got a world-class delta, plastic fan greater than 10 kilometers thick, extensive potential DSHI flat spots and AVO anomaly on 2D and 3D seismic data. It's ultra deep water, 12 to 13,000 feet. There's no wells, huge untapped petroleum potential. When I'm looking at frontier opportunities, one of the keys to what may lead you to a successful basin is the more data you collect, the better the story gets. And technologies collapse the exploration cycle. It used to take decades to find a new petroleum province. Now it can be done in a matter of years. A well's going to calibrate resisting seismic and answer the key remaining exploration uncertainties of the petroleum type, API gravity, and reservoir performance. Things can be much bigger than you think. Large structural traps and very large combination structural traps are present. Fit to structure stack, flat spots and AVO anomalies. There's few velocity pull down anomalies, which to me is indicative of small gas caps. Stacked amalgamated channel sandbelt packages 7 kilometers wide and gross Pliocene reservoir intervals 1,000 to 1,500 meters thick. That's important from what's our trap capacity. And you could trap a tremendous quantity of hydrocarbons in these reservoirs and the structural configuration of the traps. You've got large, thick, high amplitude, low frequency source rock pods telling you that you've got a way to measure what's the generative capacity of this basin. You have clear fault migration pathways with anomalous AVO signature from source to reservoir. And the basin modeling is consistent with the source rock in the main oil. Here's the caveat. Frontier exploration is only for the bold. Deep water seismic data is very good at identifying and defining petroleum accumulations, but it takes a well to prove what seismic cannot measure. Deep water and drilling production must break the 4,000-meter barrier, and my bet is on technology, and engineers are going to figure out a way to do it. Here's what technology's done for compressing the exploration cycle. In the Gulf of Mexico, between 1980, when I did this slide in 2014, there's a total of 27 billion barrels of oil equivalents been discovered out here. So it took, almost 35 years to come up with those figures. In the Rovuma Basin, between 2007 and 2014, E&I and Anadarko and their partners proved up almost 25 billion barrels of oil equivalent in gas in offshore Mozambique. It's an incredible resource value proven up in a very short period of time. And my question now is the Magdalena. Between 2014 and how much resource is going to be proven up? And I definitely think it could be in this kind of range. I want to thank everyone for your attention, and got any questions? This is our mascot for exploration in Colombia. It's the purple angel. And that concludes my presentation.
Thank you, Dr. Frost. It's been a quite interesting presentation. Okay, there are 3 questions by Luis Carlos Carvajal. Of course, they're quite nice questions. So the first question for you, Dr. Frost, is what event created the Northwest Southeast SR stripping in the Columbia Basin? What is the most likely age of those source rock pots?
I think the age of the source rocks are going to be equivalent to what is outcropping in Costa Rica. So basically, let's see if I can find it quickly. It's going to be Cenomanian through Campanian age, which roughly figures out to the source rocks that were found. The source rocks that they found, the very thin source rock. I mean, we're talking a meter here, maybe 2 meters in DSDP 153. We have another question.
Yeah, we got 2 more questions by Luis Carlos. The next question is, Dr. Frost, do you see a connection between the rich source rock intervals described into the Venezuela Basin by the DSDP 146 and the one that is located in the Beata Ridge, the DSDP 153? The Loma Chumico Formation and the untested Columbia Basin? Do you see a connection between all of those rich source rocks?
The source rock in Costa Rica, in the Tempisque Basin, that's sitting over here, and it's hard to make a correlation through what are the present day volcanics in Costa Rica. But what's really curious is right here on the border between Costa Rica and Panama, there was a well drilled on shore that it flowed about 10,000 barrels of oil, and which is documented. I don't have a sample of it's not documented, but recorded how much it flowed was. And it's really curious because where did all that oil come from? In the local area here, there's no outcrops for it. The well didn't encounter any source rocks, but it flowed oil. And to me, we've got no drilling in this basin between Costa Rica and Nicaragua and Panama. There's no deep water drilling here in Panama, but seismic data has been acquired here, and we don't see any of the kind of DHIs that we see in the Magdalena fan. But you also have this high ridge that sits out here. And I think this is one of the boundaries of this basin in Grand Col. And I don't think that, you know, when you're trying to open up this incipient ocean center, you're going to have areas that are low, you're going to have areas that are high, areas that are low again, and then areas that are high. And I think that if you want to put a story together, this is like, we have seismic ties from the Columbia Basin to DSDP 153. You can see that the interval matches what would be down underneath the fan here. So the fact that you found a meter of what could be source rock in DSDP 153 is favorable with the fact that you can tie it into these things out here underneath the Magdalena fan that you can see have a lot of difference compaction in them, which I think is what you'd get displayed in a very rich source rock basin. So it's consistent with the observations you can make, but we just don't have the data. And that's the problem is that once you drill a well, and if you're successful, nobody cares about how it works, so long as they can define where they're going to drill the next well. But when you're in the frontier exploration phase, of course, makes the story you develop from the observations you make don't have any. You have no way to verify them because you don't have the data. But you can still make predictions with your story that can be consistent with the observations you make. That becomes a very powerful tool to be successful in frontier exploration. That's about all I can say. I was just fascinated looking at the data over here in Costa Rica and their descriptions, because that's what I would imagine would happen here. The hydrothermal systems, the pillow basalts, all of these things, which in my early career exploration, I always thought, oh, oceanic crust, no source rock, not going to work, because that's an oxic environment. It's not going to be preserved. But over time, we've learned that it's when these ocean basins are opening, you have a period of time that you can get very rich source rocks developed. And I think that's what you're seeing here. Next question.
Right. So the next question is, why do you think the industry hasn't tested yet display, knowing that all of the key petroleum elements can be present into the Columbia Basin, supporting by ABO, DHI, regional source rocks, and reservoir?
You know, that's a very loaded question, but I can tell you the history of exploration in the Gulf of Mexico was one where you developed a petroleum system on shore. And then when you ran out of easy places to explore on shore, suddenly you started to explore in shallow water, close to shore. And then from shallow water, you exploited basically out to 200 to 500 meters water depth, was where technology was being created to not just allow you to explore those areas, but to develop those areas. And then there was a problem. I mean, you could only build a fixed structure in, I think the deepest one in the Gulf of Mexico is about 500 meters water depth. And you had to wait for technology engineers to come up with a system to have floating production platforms, TLPs, and now we have basically ships that you can, during hurricanes, unplug them, move into the ship and your production facility into a safe area away from the hurricane, and plug yourself back in. And we're developing fields now in 3,000 meters water depth. So exploration drives development of technology. Well, why? Because in exploration, the DSDPs have proved that drilling in 4,000 meters of water is not an issue. They've been very successful doing that. The question now is that can you drill exploration wells in 4,000 meters of water? And I think we're getting very close to that. And once you've proved up a resource, I find engineers are incredibly creative for figuring out ways to get it out of the ground. But engineers are not going to be creative and develop those systems until explorers prove that resource is there for them to develop. And that's our job. And that's what this next few years, hopefully we'll get some deep water wells drilling these amplitude anomalies to push that technology forward. Next question.
All right, thank you, Dr. Ross. The next question is by Dr. Carlos Macelari. He asks, what is the evidence that the pots that you showed us previously are filled with a source rock?
When you look at the AVO, and you can actually see the anomalies begin to develop begin to appear between the source rock and the well-developed DHI anomalies, the class 3 ones up shallower. You can actually see them start to develop up the faults. It's just incredible. And on 3D, it's spectacular.
Okay, thank you. Luis Carlos, he that asked the first question about the stripping into the Columbia Basin. He just wanted to clarify that he was asking, like, what create the stripping of the source rocks?
I'm sorry, I didn't understand that last part.
All right, so his first question that was, what events created the northwest to southeast source rock stripping in the Columbia Basin? That was a question, stripping.
I've got you. It's a chicken and the egg problem, I think. Is the Columbia Basin in situ, or did it migrate from the Pacific along with the Caribbean plate, moving to the west or to the east, and the South American plate moving west? I don't know what the answer is. All I can tell you is the observations we make. And as we learn more data is acquired. In the Columbia Basin now, thanks to the ANH and industry, we've got a really good data set that tells us about the structure of this area of the Magdalena Fan and also of the deepwater fold belt of Panama. There's a dearth of information, almost no seismic, modern seismic in offshore Nicaragua and Costa Rica. And this area of Venezuela, there's some seismic data, but it's so structurally complex, it's really difficult to really put a pervasive story together. We've got some data in this near the Hess Escarpment up through Jamaica, but it's not enough to be conclusive, I don't believe, with respect to for solving this issue of what's the plate tectonic model for how did the basement get into this area. What I can tell you, though, is that I think the Hess Escarpment is the marking a feature of a commonality, if you will, between things that are the south of it and things that are the north of it. And Tempisky Basin here, I believe, is to the south of this Hess Escarpment, which to me puts it into the same box, if you will, as the Columbia Basin. And that gives me some satisfaction that we're comparing apples and apples and not apples and oranges. But you have to let the data speak for you, is that why on this data do we see so many DHIs, and yet some of the regional, very regional lines that we see outside this area, we don't really see any robust DHIs at all. Something has to be different. And I think that thing that makes it different is what we saw over here in the Tempisky Basin in Costa Rica. And that might be is what sits underneath here. And that's, I don't know. I imagine people will still be fighting about the plate reconstructions for the Caribbean 30 years from now. But I'm hoping within 30 years from now, we'll have this huge petroleum province off of Colombia. Next question.
Okay, thank you. There's a question by Luis Ardila. Under current world political climate, when oil companies are the bad guys, how long do you think it will take for technology to be able to explore beyond the 4,000 watts of depth?
Yeah. Well, I think my personal opinion is that one of the things that COVID proved us is that people didn't need to drive their 4,000-pound vehicle to the office and back every day. People can work at home and be just as efficient in doing their job in their dining room. And that's what COVID proved, was that you could do that. And I think oil now is going to be our transition energy source until maybe Elon Musk gets his Starlink system up and running, and everybody in the world has internet access from their home, running a computer in a remote area on solar power, and the world be interconnected, and we're not having to use petroleum, which, you know, it is getting harder and harder to find. That's what's driving us into deeper and deeper water. And I think that there's enough oil sitting offshore Colombia to fulfill that role of being that transition, to get us that transition to when now everyone is working at home, and the only reason that we need petroleum fluids is to take vacations, to fly to X, Y, and Z for a holiday, and that most of our work is going to be with this, not having to use this transportation fluid just to get to and from work. I think that the future is bright for everyone, in that we will have enough transition energy to get us there. And anyway, that's my vision of the future. Anyway, next question.
Okay, thank you. And we got the last question. How old do you consider is the Caribbean basement of Colombia into your interpretation?
How long?
How old? How old?
How old?
Yep, how old? Sorry.
I think it formed probably at this probably Cenomanian time, and that's when you tried to open up this ocean basin, and then I think it failed probably at the end of Campanian time, and it started to sink. One of the really interesting things is, I don't know if my screen is still visible.
Yeah, it is.
Okay. One of the interesting things, let's get a closer pick of the basin. Okay, here we go. One of the really interesting things here is you can actually see, and I published a paper about it, I gave a presentation about it at the Geologic Society. Our 3D survey crossed over this portion of the basin up here, and you can actually see a spreading center where the mantle necks up and comes up, and there's a volcano left in the data set. But a really curious thing is there's a period of time that these, as these source rock pods were being filled, where the whole basin was surrounded by the clip up here and this high area to the west over here. And where this incipient spreading center was here, there's a layer right at the top of this fill. There's a really curious seismic reflector. Because we had the 3D, it had polygonal faulting when you took a time slice through it. And that polygonal faulting was, I think, when the basin finally failed and started to be filled up with seawater, because the seismic data distinctly changes from going from that compactable sediments to sediments now that weren't as compactable. And I think that's documenting when you started to have a thermal subsidence here, because the spreading center was no longer active. The whole area started to sink, and what used to not have seawater in it suddenly got flooded. And that's what that polygonal faulting, the event that polygonal faulting documents. And I think that probably happened at the end of Campanian time. So that from Maastrichtian, the whole area was drowning, and that's what created the carbonates on top of the volcanic highs that you saw. Oh shoot, sorry. This is when things get crazy. That's when you deposit these carbonates. That's the last gasp of the filling up of this basin. And I think that they're probably good targets. I mean, they would have been exposed or growing, possibly exposed during low stands. And you could have probably developed some pretty good porosity there. I mean, it's going to take a while to find out, or they could be absolutely tight. It's amazing to me that when you deal with carbonates on seismic data, carbonates can have really good porosity, but be just completely tight, or they can have cavernous porosity and not have any, and also be tight. So they're kind of a mixed bag. I prefer exploring in deep water anyway, and clastics, because the AVO really helps you a lot. But I don't know if that answered your question or not, but I think these are Cenomanian to Campanian, finally getting into Maastrichtian when the whole system died, and you just restarted the depositional system when the Magdalena fan started prograding out of the basin. Any more questions? We'll probably run out of time.
No, Dr. Frost, don't worry about the time. You had this soft presentation. It doesn't matter about the time. Just wanted to, no, there are no further questions from the attendees.
Yeah, go ahead.
From the ENH, we would like to thank you. I'm just going to share my screen to show all the people the next presentation that we'll have next week. It will be a quick reminder to all of the people. So from the ENH, Dr. Frost, we'd like to thank you a lot for the amazing presentation of today. I'm quite sure that all the people, even if they didn't ask, they got plenty of questions that they could be answered during these years and beyond the drill of 4,000 meters that we got. The closest one that we got is Raya 1 from Total at the Uruguay offshore. So thank you again. Thank you very much. Thanks to all of the attendees. Remind that next week we'll have our ANH workshop number 35 with our special guest, Dr. Karina Rodriguez, with the update of the seismic reprocessing into the Sinú San Jacinto onshore. Thank you. to all of you, and see you next week, and have a nice weekend. Thank you very much.
Thank you.